Right now, as you watch this, there are galaxies so far away that they're receding from us faster than 299,792,458 meters per second, faster than light, and physics is totally fine with it. What if I told you the universe has legal ways to beat light and illegal ways that sound real on YouTube but collapse the moment you do the math? Stay with me, because by the end of this video, you'll know what can outrun light, what can't, and the one idea that sounds like a warp drive cheat code, but comes with a terrifying price tag. This defies the rule most of us grew up believing. Nothing can go faster than light. And yet, the universe keeps showing us things that look like it's cheating. First, space itself expands. That means two very distant galaxies can separate faster than light without either one breaking the local speed limit. Second, some black hole jets look like they're moving faster than light across the sky. Superluminal motion. Because of geometry and timing tricks when material moves close to light speed toward our line of sight. Third, quantum entanglement makes two particles look like they share one script. Measure one here, and the other responds there in a way that feels instantaneous. So here's the question that makes even scientists slow down. If nature can produce faster than light effects, why can't we use them to send a message, cross the galaxy, and end the whole "space is too big" problem? To answer that, we need the boring rules, the rules that secretly run everything. In Einstein's special relativity, the speed of light in vacuum, c, isn't just how fast light goes. It's the speed limit for information and cause and effect through space. If you could send a signal faster than c, you wouldn't just get a faster internet. You'd get paradoxes, situations where, from some point of view, an effect happens before its cause. That's not merely weird. That's the universe letting you break logic, and physics doesn't let you do that casually. Special relativity is one of the most tested frameworks we have, and even everyday systems like GPS depend on relativity being correct to extreme precision. Here's the detail most people miss. Relativity doesn't say nothing can ever be faster than light in every imaginable sense. It says you can't locally accelerate matter or information through space past c. Locally is doing a lot of work in that sentence. This is where things get strange, because the universe has multiple speeds hiding in plain sight. There's speed through space, spaceships, particles, signals. There's the speed of space itself changing, cosmic expansion. There's the speed of a pattern, like a laser spot sweeping across a distant wall. And there's the speed of correlations, like entanglement. Some of these can exceed c without breaking relativity, but only one kind would let you do something useful. Send a message, stream a video, call home from Alpha Centauri. And that kind seems locked behind the light speed limit. So when someone says faster than light, the real question becomes, faster than light, what? Matter? Information? Space? A pattern? Or just an illusion created by how light reaches us? Now let's run this like detectives, because every FTL moment has a backstory. In 1905, Einstein publishes special relativity, and c becomes the backbone of causality. In 1915, general relativity arrives and changes the whole game. Gravity isn't a force traveling through space, it's the geometry of space-time itself. That matters because geometry can do things objects can't. In 1929, Edwin Hubble shows that distant galaxies are receding. Space is expanding. The farther away a galaxy is, the faster it appears to recede. That sounds like a violation until you realize it's not a spaceship speed. It's the stretching of the space between you and the galaxy. In the early 1980s, inflation theory adds a wild chapter. A period when the early universe's expansion was insanely rapid, effectively faster than light expansion. Not because anything outran light locally, but because space itself changed. Then in 1994, Miguel Alcubierre proposes a warp drive space-time solution. The idea is seductive. Don't move your ship through space faster than light. Move space around your ship. Contract space in front, expand space behind, and a bubble could, on paper, translate faster than light relative to distant observers, while locally the ship never breaks c. And in the modern era, the kind of 2026-era science that keeps this conversation alive, we're sharpening two tools at once. Precision cosmology missions and surveys map the universe's expansion and large-scale structure to understand what's driving it. And quantum experiments keep reminding us the universe has instant-looking behavior that feels like a loophole. Here's the cliffhanger question that every serious physicist asks when a faster-than-light claim appears. Can it carry information? Because if it can, the universe becomes hackable. All right? 3 real faster-than-light-looking effects, plus what they actually mean. First, apparent superluminal motion, the jet illusion. Imagine a lighthouse beam sweeping across distant clouds. The bright spot can move faster than light across the clouds, because it's not a single object traveling between points. It's a pattern lighting up different places in sequence. In astronomy, something similar happens with jets from black holes and active galaxies. If material is moving very close to C and angled toward us, the timing of the light reaching Earth can make the motion look faster than light. It's geometry plus near light speed, not a particle outrunning the universe's speed limit. It looks like FTL, but it can't send an FTL message because the matter and information in the jet still obey relativity. Second, quantum entanglement, instant correlations. Entanglement is the most emotionally convincing FTL phenomenon because it seems instantaneous. Measure particle A here and particle B there shows correlated outcomes, even if they're separated by huge distances. You might be thinking, so I can send Morse code instantly by choosing what happens. You can't. The outcomes are random. The instant part is the correlation structure, and you only see the correlation when you compare results using an ordinary, slower-than-light channel. Quantum mechanics is weird, but it has a built-in safety rail often described as the no-signaling constraint. Entanglement doesn't let you transmit usable information faster than light. Third, the expansion of space, the legal way to beat light. This is the one that melts people's brains. In an expanding universe, 2 distant galaxies can separate faster than light because the space between them is stretching. Relativity forbids locally outrunning light in your neighborhood. It does not forbid the distance between very distant points from increasing faster than CE due to space-time dynamics. That's why cosmologists distinguish between an object's local velocity and its recession velocity, due to expansion. If you want a mental image, imagine running on an airport moving walkway. Your legs have a speed limit, but the walkway can carry you across the terminal faster than your legs alone ever could. In cosmology, the walkway is space-time expansion. So is there something faster than light? Yes. Space can expand so that distant objects separate faster than light. Patterns can appear to move faster than light. Correlations can look instant. But none of these let you send a usable message faster than light. And that's both satisfying and infuriating because it leaves one last category. The stuff that could change everything. Warp drives and wormholes. Warp drives and wormholes are tempting because they try to use the expansion trick deliberately. Don't break the local speed limit. Move space-time. In the Alcubierre idea, the bubble moves, not the ship. In wormhole fantasies, you take a shortcut through space-time geometry. But here comes the catch of the century. These ideas seem to require exotic conditions, often described as negative energy density or violations of certain energy conditions, stuff we do not know how to create or stabilize on macroscopic scales. Yes, quantum physics allows weird vacuum effects in tiny setups, like the Casimir effect. But that's not a warp bubble fuel tank. It's like saying a spark proves you can power a city. And now the twist that keeps this topic alive. We don't fully understand the ingredients that control space-time itself. In the mid-2020s, heading into the 2026 era, precision cosmology is getting sharper. Scientists are mapping billions of galaxies and the universe's large-scale structure to pin down the expansion history and the nature of what we call dark energy. That isn't just more data. It's us interrogating the mechanism behind the space expansion loophole. And the debate gets spicy because there are multiple competing explanations. Dark energy could be a cosmological constant, a dynamic field, or a sign that our theory of gravity needs modification on the largest scales. Scientists aren't baffled in a "we have no idea" way. They're baffled in the most dangerous way. We have multiple plausible ideas and not enough decisive evidence yet. Then there's the biggest unfinished bridge in physics. Quantum mechanics and general relativity both work incredibly well, but they don't naturally merge into one clean theory. If there's any place new rules could appear, any place where our assumptions about space, time, and information might change, it's at that intersection. That's where people start chanting wormholes, because wormholes are mathematical solutions that appear in general relativity, but allowed by equations is not the same as exists in nature or can be built. Stability seems to demand exotic energy, and we don't know if the universe permits macroscopic traversable wormholes at all. And here's an even deeper layer. In modern theoretical work, space-time geometry and quantum information appear connected in surprising ways. That doesn't give you an FTL texting app, but it hints that what we call space might be more like an emergent network than a fixed stage. The universe could be stranger than our current language can easily describe, without ever letting us break causality, so we're stuck in a thrilling place. Relativity has not been broken. No confirmed faster-than-light information transfer exists, but the stuff controlling space-time, expansion, vacuum energy, the quantum structure of reality, still has open questions. And that keeps the door cracked open just enough for curiosity to breathe. I genuinely want to know what you think. If there is a way around light speed someday, which route feels most plausible? Option A: we never beat light, only get close and accept the limit. Option B: we exploit space-time itself, warp drive or wormhole physics. Option C: quantum reality hides a loophole we don't understand yet. Comment A, B, or C and tell me why. I'll read the comments and pin the smartest explanation, because this affects all of us more than people realize. The speed of light limit is basically the universe's tax on ambition. Talking to Mars already means minutes of delay depending on where the planets are. Reaching the nearest star at even a fraction of C becomes a multi-decade project. Building an interstellar civilization without FTL becomes a question of patience, autonomy, and engineering, how you design ships, societies, and communication when instant is impossible. But it's also empowering. Knowing the rules lets us design around them. Near light speed travel is still insanely powerful. Time dilation becomes a tool. Beamed propulsion concepts, laser sails, nuclear propulsion research, and better power systems are where real space tech fights happen. And as science progresses, mapping space-time, probing quantum behavior, measuring gravitational waves, we keep testing whether any cracks exist in our understanding. The hopeful takeaway is that we don't need magic to do epic things. We can explore the solar system with today's physics. We can image black holes. We can measure space-time ripples from colliding neutron stars. We can keep pushing closer to the limits, while staying honest about what the limits are. Science makes progress not by breaking rules for clicks, but by learning which rules are real, which rules are local, and which mysteries were just misunderstandings. But this isn't the only mind-bender hiding in modern physics. Next up, how a warp drive would actually work in the math, why time dilation is basically a real-life cheat code, and the strangest thing about quantum teleportation that almost nobody explains clearly. Subscribe so you don't miss those. Thanks for watching. The universe doesn't just limit speed, it protects cause and effect. And that might be the most important safety feature reality has. Stay curious, and I'll see you in the next one.